Hi everyone, I'm Emanuele Albini, and this is a joint work with Jason, Danial, and Daniele, all of us from JP Morgan AI Research. And as the title suggests, this work fits into this line of research that has been developing recently that try to unify, on one side, feature importance explanations, and in particular in this work, SHAP, and on the other side, counterfactual explanations. So let's start by first listing very briefly what are the limitations of these two kind of approaches that we are trying to overcome in this work. And let's start by imagining that we are in the classic explainability scenario. So we have a machine learning model, and this model has rejected a customer for a loan application, let's say, because the predicted probability of default is too high. Now, if we ask a sharp explanation, what we get is a feature importance. And this feature importance is basically telling us how much each of the features increased or decreased the predicted probability of default for this customer. Now, there are two main limitations with this approach, and the first limitation is that it doesn't provide the explicit guidance on how a user might then alter their behavior in order to overcome the rejection. If I've been rejected for a loan, I want to understand what features I can change, how much I can change them, and in which direction I can change these features, if I have to increase them or decrease them in order to change the prediction from a rejection to an acceptance. The second observation that we can do about this approach is that it requires the definition of what a missing feature is. And in other words, it requires to define what it means to remove a feature from the model. And while this is very obvious in game theory, because we just remove the player from the game, it's not really clear what it means in a machine learning model to remove a feature from the model. And the observation that we can do here is that typically in the literature, what people do when removing feature is that they replace their value with some values that are extracted from some background distribution of points. And what people typically use as background distribution of points is the training set. So what really is happening when we are asking a sharp explanation is that we are contrasting this client that have been rejected with this background distribution of clients. So the explanation is really telling us what features were most important in rejecting this client according to the model when compared to all these other clients in the background distribution. And let's now move on to the second class of approaches that are counterfactual explanations. Here, together with the prediction of a client being rejected, we also get a counterfactual point that is basically a point that is very similar to the original input, but that has some feature changed. And this changed feature allows the model to change its prediction from a rejection to an acceptance. Now, there are some limitations also here, and the first limitation of counterfactual generation algorithm proposed in the literature is that most of them provide only a single counterfactual point. And having a counterfactual is a very useful information, but having a single one do not allow a user to really choose the counterfactual that best suits them. If I'm a user, I may not want to change my balance, but I would like to know how I can change my income, for example, in order to overcome the rejection. So for this precise reason, some people have proposed in the literature the generation of diverse counterfactuals. But if we generate multiple counterfactuals for a single client, then other limitations arise. And the first one is that there is not really a consensus on how to summarize all this information that we provide to the client. Let's imagine that we have a very complex model with dozens of features and we are providing hundreds of counterfactuals. It's very cognitively demanding for a client to understand what's going on there and what's the best course of action in order to overcome the rejection. The second thing that we get when we generate a lot of diverse counterfactuals for a lot of clients is that we may leak information, and we may leak information both about the model that in certain situations may not be really desirable, or even at a certain degree about the training data itself. So what we propose to unify these two types of explanations, counterfactuals and sharp, and consequently overcome some of the limitations that I've highlighted now, is to still generate a feature importance explanation based on sharp, and this explanation is therefore very compact and easy to understand for a potential user of this explanation. But contrary to the standard sharp, we change the background distribution from the training set to some counterfactual points. And what happens if we do that is that we are now comparing a client text that has been rejected with similar clients that have though been accepted. So instead of comparing a client text that has been rejected with much worse clients or with much better clients, we will be only comparing client text with clients similar to them but that have been accepted. So let's now look through an example at what happens if we do that. And let's imagine that we are in a toy setting again, in which we have two features, current account balance on the x-axis, income on the y-axis, and we have a machine learning model with a decision boundary described by this black line, and a client text that has been rejected because they are on the red part of the decision boundary, while the blue part represent acceptance. Now, let's try to generate explanations using different background distributions. So let's start by using a background distribution of points that are all the accepted customers of the model. So all these small dots represent all the accepted customers by the model. And our client text that has been rejected is instead here in the red part of the plot. The arrow here represents the direction of the Shapley value vector. And what we can see if we look at the Shapley value is that the second feature, income, the feature on the y-axis, is deemed as the most important feature for rejection because it's increasing the probability of default of this client the most. While the first feature instead here is deemed as slightly protective against the rejection because it has a negative value. Now, this explanation totally makes sense if we look at the background distribution of points. And in fact, we see that the second feature, income, for this client text is much worse than the income feature for most of the clients in the background distribution. And for this reason, Shapley values are telling us that income is the main driver for the rejection. If instead we look at the first feature, current account balance, we clearly see from the plot that the current account balance of this client is not that much worse from the current account balance of all the other clients that have been accepted. It's around the mean of the current account balances for these accepted clients. So this explanation totally makes sense, it's useful, and it's telling us what are the main drivers for the rejection of this client. But it's very clear that it's not telling us what features we should change in order to go on the other side of the decision boundary. And again, if we look at the plot, it's very clear that if we want to jump on the other side of the decision boundary, it's much easier to change the current account balance than changing the income. So let's now look at what happens if we instead use as background distribution of points for SHAP some counterfactuals. And we see immediately that the direction of the Shapley value changes to something that is pointing more towards a change in the current account balance. And if we look at the Shapley values themselves, we see indeed that the first feature, current account balance, is deemed as more important than the second feature, income, in order to get on the other side of the decision boundary. So here we are two different explanations, both valid explanations, but the first explanation is telling me the main drivers for the rejections, while the second explanation is really telling me what features I should act upon in order to go from a rejection to an acceptance. And to do that, it's looking to customers that are similar to me but that have been accepted by the model. Using counterfactuals as background distribution of points for SHAP, we now know what features we should change in order to go from a rejection to an acceptance. But we still do not know the direction in which we have to change those features. And for some feature, we could be in certain situation in which we do not know if we have to increase the feature or decrease the feature in order to change the rejection into an acceptance. For example, in this toy example, we see that there are two customers, and for both the customers, the first feature, feature A on the x-axis, is the most important feature according to the Shapley values. But for the first customer, the features must be decreased, while for the second customer, the features must be decreased. So what we propose here is to enrich the explanation of SHAP with some derived trends that are basically describing if I have to increase or decrease the feature. And a value of +1 means that I have to increase it, a value of -1 means that I have to decrease it. And these values are extracted by the counterfactuals. If most of the counterfactuals says that the features must be increased, then I will tell the client to increase it. If most of the counterfactuals are saying that the features must be decreased in order to go on the other side of the decision boundary, then I will tell the client to decrease it. So if we do all this, we will know what are the values of the features for a client that has been rejected. We will also know what features we should change in order to go from a rejection to an acceptance. And we will also know if we have to increase or decrease those features in order to achieve an acceptance. And the only question that is left to be answered is, how do we evaluate this kind of explanations? So what we also propose in our paper is a flexible evaluation framework for any kind of feature importance explanation. And the idea of this framework is basically that we can make some assumptions about the user behavior, and in particular we can make some assumption about how the user will interpret our explanation. So, for example, here I'm showing one instance of our more general framework in which we assume that the user will change their feature proportionally to their Shapley values. So if the user received this kind of explanation in which the first feature is slightly more important than the second one, what the user will try to do is to change feature A, the first feature, more than the second features on the y-axis. And what happens is that if the user follow the suggestion of the explanation of increasing their features proportionally to their Shapley value, at some point they will reach the decision boundary. And when they reach the decision boundary, we will find a point x prime that we call induced counterfactual by the explanation. And the idea is that once we have this point, we can check several metrics from the counterfactual literature on the gooseness of this point. One of the metrics that we can check is, for example, the cost of the induced counterfactual. And the expectation here is that a good explanation will be giving us an induced counterfactual that has a lower cost, while a bad explanation that is not able to point us in the right direction will give us an induced counterfactual with a higher cost. So what we did is that we used the total percentile shift as a metric for the cost, and in our experiment we showed that varying the number of features that a user is allowed to change, we can almost always see that our explanations perform better than the baselines. In this plot, 0% represent same cost as the baselines, and anything above 0% is better than the baselines. So we can see that in different data sets and allowing different numbers of top features to change, our explanations always have a lower cost. Another metric that we can check is also the plausibility of counterfactuals. And again, here the expectation is that an explanation that is a good feature importance explanation will be suggesting to change features that give you high plausibility in the induced counterfactual. And here we measure plausibility using the distance from the 5 nearest neighbors. And we obtained in the experiment similar results to the one that we obtained for the cost of the induced counterfactuals. So 0% is again a similar performance to the baselines, and we see that in almost all settings among different datasets and different number of top features allowed to change, we have that our explanation has higher plausibility than the baselines. To summarize, what we did in our paper is, first of all, to propose counterfactual SHAP, that is a variant of SHAP in which we use counterfactual points as background distribution. And this allows us to get a feature importance that highlights better the features that are truly important to go on the other side of the decision boundary. And secondly, we also propose a modular framework to evaluate these feature importance explanations, and in particular to evaluate how good are they to provide the features that allow a user to go on the other side of the decision boundary. We have a couple of future research directions, and the first one is testing our framework with different counterfactual generation engines. In fact, in our paper, we focus only on one. And secondly, explore different assumptions about the user's behavior. In our paper, we propose 2 of them, but of course, there could be many more that make sense. If you have any question, please reach out to me with an email or check out my website with my contacts.